Ectomorph. You may have spent most of your life hearing the same sentence repeated again and again. You just need to eat more. To the people saying it, the explanation feels obvious. If weight does not increase, then effort must be missing somewhere. But this interpretation assumes that every human body is designed with the same priorities, and evolution tells a very different story. What appears in the modern world as difficulty gaining mass can also be understood as the visible trace of an ancient survival strategy. The ectomorphic build is not primarily a body made for storing energy or displaying strength. It is, above all, a body organized around endurance. To understand why this matters, we have to step back tens of thousands of years to a time when early humans lived in open, sun-exposed landscapes where survival depended less on technology and more on physiology. On the African savannah, humans were not the fastest predators, nor the strongest. They lacked claws, fangs, and the explosive power that many animals relied on for hunting. And yet, despite these disadvantages, they managed not only to survive, but to become one of the most successful species on the planet. One of the keys to this success was a hunting method that researchers now call persistence hunting. Instead of attempting a rapid kill, hunters would track an animal and pursue it over extremely long distances, sometimes for several hours under intense heat. The prey, often built for short bursts of speed, could escape quickly, but struggled to cool its body during prolonged effort. As the chase continued, the animal's internal temperature rose gradually until its physiology began to fail. Muscles lost coordination, breathing became unstable, and eventually the animal collapsed from exhaustion and overheating. The human hunter, however, could keep going. This capacity was not accidental. A relatively lean body dissipates heat more effectively because it carries less insulating tissue and exposes more surface area relative to total mass. Lower muscle volume produces less internal heat during sustained activity, and efficient sweating enhances cooling through evaporation. Together, these traits form a physiological system optimized not for explosive strength, but for continuous motion across distance and time. Of course, such specialization involves compromises. A fast metabolism requires regular access to food, and limited fat reserves reduce protection during famine or prolonged illness. In environments where calories disappear for long periods, this same body that excels in heat can become vulnerable. Yet in hot regions where endurance determined hunting success and food sources were relatively consistent, this design proved extraordinarily effective. It allowed humans to outlast animals that were faster, stronger, and more heavily built. Over generations, that advantage was enough to shape survival itself. When the sun remained high and the chase stretched beyond exhaustion, the bodies that could continue moving were the ones that endured. And that endurance is still written into the ectomorphic form today. Endomorph. If the ectomorphic body reflects survival through endurance, the endomorphic body reveals survival through storage. In contemporary culture, higher body fat is often interpreted almost exclusively through the lens of health risk or personal responsibility. Evolutionary history, however, frames the same trait in a radically different way. For most of human existence, the greatest and most constant threat was not violence or predators, but the simple absence of food. Seasonal cycles, droughts, failed hunts, and long migrations repeatedly exposed human populations to starvation. Under these conditions, the ability to store energy efficiently was not a disadvantage. It was a decisive advantage. Bodies that conserved calories, slowed metabolic expenditure, and converted excess nutrition into fat reserves could survive weeks or even months with little external food. What modern language sometimes labels a slow metabolism once represented a powerful form of biological resilience. Genetic research provides striking illustrations of this principle. Certain Pacific Island populations carry variants commonly referred to as thrifty genes, which enhance the body's tendency to store energy. In today's environment of continuous food availability, these same variants are associated with increased obesity risk. But in ancient contexts, such as long ocean voyages lasting weeks with minimal nourishment, they could mean the difference between life and death. Fat tissue also plays multiple protective roles beyond simple energy storage. It provides insulation against cold, supports immune function during illness, and supplies critical reserves during pregnancy or injury. When famine struck, individuals with stored energy simply survived longer, allowing their genetic line to continue while others disappeared. Seen from this perspective, the endomorphic build is not evidence of biological failure, but of historical success. It represents adaptation to a world defined by uncertainty, where survival depended on preparing for scarcity long before it arrived. The same efficiency that creates challenges in an age of abundance once protected entire bloodlines from extinction. This body was shaped not for supermarkets or permanent access to calories, but for empty seasons and unpredictable survival. And in those silent periods when food vanished, the bodies that had stored energy were the ones that endured. Mesomorph. Between endurance and storage lies another evolutionary pathway: force. Some individuals develop muscle easily, gain strength rapidly, and maintain an athletic structure even with limited training. From a modern viewpoint, this may look like simple genetic luck, but evolution rarely preserves traits without reason. Mesomorphic bodies tend to contain a higher proportion of fast-twitch muscle fibers, specialized for explosive movements such as sprinting, striking, and lifting heavy loads. These fibers sacrifice long-term endurance in favor of rapid, high-intensity power, exactly the kind of output required in moments where survival is decided in seconds. Early human communities depended on individuals capable of confronting predators, hunting dangerous animals at close range, defending territory, and constructing shelters strong enough to withstand harsh environments. In such contexts, physical strength was not aesthetic. It was protective, practical, and often life-saving. This body type also responds strongly to resistance training and converts dietary protein into muscle with notable efficiency, suggesting long evolutionary pressure favoring individuals who could quickly build usable strength when circumstances demanded it. Yet specialization again brings trade-offs. Greater muscle mass increases caloric requirements and internal heat production, making prolonged endurance in extreme heat more difficult and periods of famine more dangerous. No evolutionary solution is universal. Each represents a balance shaped by specific environmental pressures. Still, when survival depended on decisive physical power delivered at the right moment, the mesomorphic build offered a clear advantage. And that advantage was enough to persist across generations. Small frame. Across diverse regions of the world, evolution repeatedly favored smaller body size in environments where resources were limited or unpredictable. While modern perception sometimes equates size with strength or capability, biological reality often rewards efficiency instead. A smaller body requires fewer calories for maintenance, less oxygen for activity, and reduced overall energy expenditure. Over extended periods of scarcity, these differences accumulate into powerful survival advantages. Anthropological evidence reveals higher frequencies of shorter stature among populations living in tropical forests, isolated islands, and high-altitude regions, places where food distribution is scattered and conservation of energy becomes essential. Reduced body mass can also enhance agility, balance, and climbing efficiency, traits valuable in dense vegetation or mountainous terrain. Although absolute strength may be lower, survival in these environments rarely depended on brute force alone. It depended on the ability to function longer with fewer resources. When food is scarce, needing less becomes a form of power. And in ecosystems that could not sustain large bodies, small size became not a weakness, but an elegant evolutionary solution. Large frame. If smaller bodies reveal the power of efficiency, larger bodies tell a different evolutionary story, one written not in heat or scarcity, but in cold. To understand this adaptation, we need to imagine environments where survival is defined less by hunting success and more by the simple ability to remain warm. In Ice Age Europe, in Arctic tundras, and in windswept northern plains, temperature alone could decide whether a human being lived through the night. Long winters reduced plant life, migration routes shifted, and exposure to freezing air became a constant biological threat. In such conditions, physics begins to shape evolution in unmistakable ways. Heat leaves the human body through the skin. When overall body mass increases faster than surface area, warmth is retained more effectively. This relationship, sometimes summarized in biological rules about body size and climate, helps explain why populations living in colder regions have historically tended toward taller stature, broader bones, and greater overall mass. A larger frame is not merely about strength or appearance. It is, at its core, a thermal strategy. By conserving internal heat, larger bodies reduce the energy required to maintain stable body temperature. This matters enormously in environments where food is limited and calories must be used carefully. Retaining warmth can mean the difference between gradual survival and slow hypothermia. But the story does not end with temperature. Greater body size also supports increased muscle mass, which in turn enables the handling of heavy materials, the transport of resources across snow-covered terrain, and the hunting of massive Ice Age animals such as mammoths or woolly rhinoceroses. Shelters strong enough to resist winter storms required force to build. Clothing made from thick animal hides required strength to prepare. Even daily movement through deep snow demanded physical power. In this context, size becomes more than protection. It becomes capability. Of course, this adaptation carries clear costs. Larger bodies require more calories to sustain basic metabolism, and in warmer climates, they face a serious risk of overheating. What protects survival in freezing environments can become a liability under intense heat. Yet evolution does not seek perfection. It selects what works where it works. And in frozen landscapes where smaller bodies lost warmth too quickly to endure, greater size was not excess. It was survival itself. Hybrid build. After exploring bodies shaped by endurance, storage, power, efficiency, and cold resistance, one final evolutionary pattern emerges, less obvious, but perhaps the most profound of all. Not every human body is specialized. Many people exist between extremes, carrying moderate endurance, moderate strength, and moderate energy storage. From a modern perspective, this can appear unremarkable, as if lacking the dramatic advantages seen in more specialized physiques. But evolution often rewards something quieter than dominance. It rewards adaptability. To understand why, we must consider the greatest challenge faced by early humans. It was not simply heat, cold, or famine in isolation. It was change. Across tens of thousands of years, climates shifted repeatedly. Ice ages advanced and retreated. Forests expanded, then vanished. Animals migrated, disappeared, or evolved. Human groups themselves moved into entirely new environments, encountering unfamiliar dangers and unpredictable resources. In stable conditions, specialization can be powerful. Bodies optimized for endurance dominate long hunts. Bodies optimized for storage survive famine. Bodies optimized for strength win violent encounters. But when conditions transform rapidly, extreme specialization can become fragile. A body perfectly adapted to one environment may struggle when that environment disappears. This is where the hybrid build reveals its hidden advantage. Balanced physiology allows a person to run reasonably well without sacrificing all strength, to store some energy without losing all mobility, and to generate force without extreme caloric demand. It is not the best at any single task, but it is rarely the first to fail when circumstances change. Across unpredictable environments, this flexibility becomes a powerful survival tool. Communities containing adaptable individuals are more likely to persist through migration, climate fluctuation, and shifting food sources. Over generations, that persistence shapes evolution itself. In this sense, the hybrid body represents not a compromise, but a strategy of resilience, a design built to endure uncertainty rather than dominate stability. And across the long, unstable history of our species, resilience has often mattered more than perfection. Every body that exists today is proof that survival happened. Different forms solved different ancient dangers: heat, cold, hunger, distance, uncertainty, and change. Your body is not a mistake. It is history, written in biology. Explaining things simply.